This nice proof of the existence of black holes in the universe for the disbelievers in the audience. And these are the orbits of stars at the center of our own galaxy, and they are very nice ellipses revolving around some central object that we don't see. And from the shape of these ellipses, we can infer that there has to be a very concentrated mass of about 4 × 10⁶ solar masses at the center of our own galaxy. However, it's very hard to show by electromagnetic observations that the object at the center of our own galaxy is actually a black hole. So what I'm going to talk about today is how we can use gravitational wave observations to do black hole spectroscopy, that is, to identify the objects that we see out there and which are too compact to be something else, as being the black holes of general relativity. And this is the outline of my talk. First of all, I'm going to give a very brief introduction to perturbation theory and to the concept of quasi-normal mode ringing. And then I will explain how to carry out tests of the general relativistic no-hair theorem. We need at least to measure 2 of the quasi-normal modes, 2 quasi-normal mode frequencies from a black hole. And I will also argue in the first part of my talk that the 2 key ingredients that determine whether we can detect and measure the quasi-normal mode frequencies are the spin of the remnant formed as a result of a binary black hole merger and the ring-down efficiency, that is, the fraction of the total mass which is radiated in ring-down modes. And then, in the second part of my talk, I will go through recent results from numerical relativity simulations of merger simulations, from numerical relativity simulations of merger of binary black holes. And I will tell you how these simulations can now be used to give us this information, the final spin and the ring-down efficiency. I will also try to tell you something about the implications of the results of numerical relativity for astrophysics. And in the third part, I will tell you something about how we can try, what kind of performance we should expect when we try to detect waveforms that contain more than 1 quasi-normal mode by templates which consist of a single quasi-normal mode. What kind of parameter estimation bias we're going to get, and a possible cure to the parameter estimation bias, which consists in the use of Prony methods. Finally, if I have some time at the very end, I'm going to tell you something about simulations that we're looking at right now of the boosted head-on collision of 2 black holes. And these seem to be the most relativistic processes we've looked at so far. In fact, the energy emitted in these processes seems to be saturated in the area theorem. So, first of all, a very brief introduction about the astrophysics of the process we have in mind. What we have in mind is, for example, the formation of a binary, also of a supermassive black hole binary. And the idea is that you have 2 black holes at the center of their own galaxies, like the supermassive black hole that I've shown you in the movie. And these black holes, now we think that galaxies are formed by repeated mergers, grow by repeated mergers. And when you had 2 black holes at the center of each galaxy, these 2 black holes sink to the center of the 2 galaxies by dynamical friction. And then there's a second phase where gravitational slingshot interactions increase the binary's binding energy. And when, by a combination of these processes, the 2 black holes are really close together, gravitational radiation reaction takes over, and the black holes get together because of gravitational radiation emission. And depending on the mass ratio of the 2 black holes and on their spins, there can be a very large recoil velocity that eventually could even kick the black holes out of the host galaxy. Now, there's an important uncertainty in this astrophysical scenario, which is well accepted, I would say, at this point. And the main uncertainty, in my view, is the way you start this whole process of repeated mergers of black holes. Now, there are 2 scenarios which are quite popular out there. There are actually more than 2 scenarios, but to simplify. In one scenario, you start with black hole seeds that are formed by the collapse of population 3 stars. So you have stars of mass between 30 and 300 solar masses. These stars collapse and they form a black hole. And these black holes typically have a mass of around 100 solar masses. And then they grow by accretion and repeated mergers until they form the supermassive black holes that we see at the center of galaxies today. And in a second scenario, for example, you can consider that these seed black holes are actually formed by the direct collapse of low angular momentum material in progalactic disks. In this case, you start with black holes of much larger mass, of order 10 to the 5 solar masses, and at much larger redshifts. And these black holes are already in the wave band of LISA when they are born. So you expect the rates in the second scenario to be much larger than the rates in the first. And in fact, this is a table that I prepared for a short review that I wrote a couple of years ago, where I show the rates for detections by LISA, depending on different formation scenarios for supermassive black hole binaries. And you see that the numbers are pretty much all over. They range from 1 to about 10 to the 5. And now the general wisdom is that we should expect to see at least 10 events with a good chance that we could even see hundreds of events, depending on how lucky we are. And also, various people have proposed the idea that we could also be able to observe with LISA the coalescence of intermediate mass black holes into supermassive black holes. So this was just to give you a flavor of the kind of astrophysics we want to do with the observation of supermassive black hole mergers and ring downs. Now I'm going to talk about the theory, and I will give you a very brief introduction on black hole perturbations. In fact, I'll try to squeeze all of black hole perturbation theory in one slide. And the idea is that people started studying black hole perturbation theory because they were interested in the stability of black hole solutions of general relativity. So what they did is they considered linear perturbations of the background black hole metric, which are induced by some field, a scalar field, electromagnetic field, or a gravitational field. And then the general procedure technically consists of these steps. First of all, you separate the time dependence of the perturbations by using Fourier transforms. Then you separate the angular dependence of the perturbations using some special functions that are scalar, vector, or tensor spherical harmonics. Just think of the ordinary spherical harmonics. This step actually doesn't work for curved black holes because the background is not spherical, and you have to use something called the speedway spheroidal harmonics. And then you end up with a set of radial equations. And these radial equations can be combined to give a single Schrödinger-like equation that, depending on the parity of the perturbations, is called Regge-Wheeler equation or Zerilli equation. And this is the way the wave equation looks. It's basically a Schrödinger equation with the frequency squared playing the role of the energy. And there's some potential V on the right that depends on L, which is the angular index in the spherical harmonics, and on the spin of the perturbation. From now on, we will only consider gravitational perturbations because we're looking at gravitational waves. And a remarkable thing that was discovered by Chandrasekhar is that the potentials for axial and polar, even and odd in terms of parity perturbations, they look really different, but they give, they produce the same spectrum of quasi-normal modes. The spectrum of quasi-normal modes was discovered in the following way. People in the 70s, once they found this very nice wave equation, they started studying the scattering of waves of a black hole. And they started by studying Gaussian pulses of radiation. And what they realized is that the radiation coming out of the hole is discrete, and it has a spectrum of modes that, in the case of Schwarzschild, is determined only by the mass of the hole. And then people started studying more fancy processes going on in black hole backgrounds. For example, this plot refers to a particle falling radially into a Schwarzschild black hole. And this is the gravitational waveform emitted. It has a precursor phase, a burst of radiation, and then the radiation falls down as a damped exponential, where the fact that you have a well-determined frequency depends on the particular black hole you're looking at, and the damping is due to the emission of gravitational radiation by the black hole that is vibrating like a bell. And these modes are basically associated to the fact that there is a peak in the potential describing the space-time curvature around the hole. And since you're really studying a problem of scattering on a potential, you can use techniques that come from from quantum theory. And for example, you can use WKB methods, you can use phase integral methods, and you can use some more fancy ideas to obtain the quasi-normal mode spectrum of black holes. I don't have time to talk about this, but I will show you what the spectrum looks like. And so remember that you have separated the angular dependence by using some angular functions that depend on angular quantum numbers L and M. And for each L and M, you will have an additional sum over n, which is an index describing the overtone number of the whole. Basically, this index starts from n equals 0 or n equals 1, depending on the conventions down here, and it grows as the imaginary part of the modes grows. So the mode down here is the one which has the smallest imaginary part and the longest damping time, and it's the mode that we expect to be dominant in gravitational radiation. We expect this particular mode to be dominant because we know that gravitational radiation is predominantly quadrupolar, and because this is the mode which has the longest damping time, so we expect it to live longer. Now, an interesting thing is that if you plug in physical numbers, what you realize is that the frequency of this fundamental mode down here for a Schwarzschild black hole is of order 10 to the minus 2 hertz for a black hole of 10 to the 6 solar masses, which means that if we consider a black hole of the kind that is thought to live at the center of our own galaxy, the frequency of the quasi-normal modes emitted by this black hole is in the sweet spot of LISA, for example. And the damping time for this black hole would be something like 1 minute. Now, this spectrum is a discrete spectrum that refers to a Schwarzschild black hole. Now, suppose that we look at this particular mode, but what I'm going to say applies to all modes in the spectrum, and we consider a rotating black hole now. What happens when we consider a rotating black hole is that, well, it's very similar to what happens to an atom, to the energy levels of an atom when it's immersed in an external field. There's a sort of Zeeman splitting of the modes. So the perturbations are not degenerate with the azimuthal quantum number anymore. And in fact, this point here that was the quasi-normal mode frequency of the Schwarzschild hole splits into 2m plus 1 modes. So where in this case we have 5 because we are considering L equal 2. And so the modes move out, and for each value of the rotation of the hole, we will have a different frequency depending on m. And in particular, I will show you from numerical relativity simulations that the L equal m equal 2 mode is the one which is thought to be dominant. And for the L equal m equal 2 mode, you can see here that as the rotation increases, the imaginary part tends to 0 eventually at the end of this plot. And which seems to suggest that when the black hole becomes extremal, it also becomes marginally unstable. In fact, this turns out not to be the case. All Kerr black holes are stable. But now, since the frequencies for a given mode depend on the mass and on the angular momentum, if we can measure both the real part of the frequency and the damping time, then this means that we can also measure the mass and the angular momentum of the black hole. And this idea, in fact, was proposed at the end of the 80s by Echeverria, and then also Finn explored it. The idea is that if you know which mode you are measuring, for example, if you know that you are measuring the L equal m equal 2 mode, from the frequency and the damping time, which are known functions of m and j determined from perturbation theory, you can find m and j. But now suppose that you measure not only one mode, that you measure 2. The first mode will give you m and j, but then all the other modes are fixed by the theory, and detecting the frequency or the damping time of the second mode gives you a test of general relativity. And the more modes you detect, the more tests of consistency you have. Now, I will show you in the following of my talk that under reasonable assumptions, being able to measure to a decent accuracy the first and the second mode requires a signal-to-noise ratio of order between 10 and 100. This means that the test, in principle, is possible if we have a detection not only with LISA, but also with advanced LIGO, or in general, Earth-based detectors of second generation. And this test is very similar in nature. Yes?
So if the ring down is preceded by an in-spiral,
yes,
which also gives you information on M and J.
That's a very good point. Yeah.
Does that help?
Of course it does.
Can you still do tests without having one mode?
Of course, it does help you because it constrains. In fact, there are papers out there studying how you can improve parameter estimation from both phases by combining information.
Because the strong frequency dependence of the noise in, say, LIGO and LIGO means that it's, if you see one in the sweet spot, the other won't be.
Yeah, that's definitely true, and I will say something more about this. Yeah, I hope to get there and to show you what happens if you try to. In fact, only one is going to be there, and if you try to detect a waveform in which there is more than one mode by using a template that has only one mode, you may well end up in the wrong spot. I will show you something about that later if I have time. So for the moment, just let me show you. Let's suppose for the moment that we only have one mode, and the signal-to-noise ratio will be computed by the usual integral that depends on the spectral noise density of the detector. And in this particular case, I'm showing you the signal-to-noise ratio as a function of the total mass of the hole. And these are the dashed lines. And the continuous lines are the in-spiral signal-to-noise ratio for an equal mass merger. So what you can see is that typically, if you consider, suppose that you consider the in-spiral of two equal mass holes at redshift 0.5 that corresponds roughly to 3 gigaparsecs. Now, the signal-to-noise ratio for in-spiral in LISA can be as large as a few thousands, and the signal-to-noise ratio for ring-down can be of order 10 to the 4 even. And of course, the signal-to-noise ratio goes down with luminosity distance, or if you like, it goes down with redshift. But in a redshift 10, which means very far away, the signal-to-noise ratio is still of order, can be for ring-down of order a few hundred. And of course, these numbers that I'm showing here, they depend on what we assume for the ring-down efficiency. This 1% is very well justified, and I will try to show you later why, and also on the spin of the hole. If you want to know how these numbers will change under different assumptions for the ring-down efficiency and the spin of the hole, this is what you would get for an efficiency of 3%, which is quite optimistic, and this is what you will get for an efficiency of 0.1%. And the solid dashed and dashed dotted lines, they refer to black holes which are spinning with zero spin, so a Schwarzschild hole, 0.8, and 0.98, which is very close to the maximum achievable by astrophysical processes. So basically, the point is that spin produces a shift in the mass range that you can detect, and it's really the ring-down efficiency that determines what kind of signal-to-noise ratio you can achieve. What can we do with Earth-based detectors? Well, this plot shows the signal-to-noise ratio for a binary which is, sorry, for a black hole which is located at 100 megaparsecs. And what you see here is that this black hole would be barely detectable by LIGO and Virgo, first generation LIGO and Virgo, but it would be detectable with a signal-to-noise ratio of order 100 or more by advanced detectors. And also notice the mass range. If we detect ring-down waves with Earth-based detectors, this could well be the first experimental proof of the existence of intermediate mass black holes, which is subject of debate in the astrophysical community. And you can also look at this plot the other way around. You can suppose that you want a signal-to-noise ratio of 10, and this is the reach in luminosity distance that you would get for initial detectors and advanced detectors. With advanced detectors, you can do something like 1 gigaparsec for black holes of mass between, say, 10 to the 2 and 10 to the 3. Okay? Now, let's go beyond detection and let's talk about measurability of the frequency of the quasi-normal modes. Now, a very simple way to assess whether you can determine the parameters of a gravitational wave with some accuracy is based on the Fisher matrix formalism. And the idea is that you have a certain model of your signal. So you have a waveform H that depends on a set of parameters lambda I. In the case of a ring down, these parameters would be the mass, angular momentum of the hole, the spin orientation of the hole, and the sky location. And then if in the limit of high signal-to-noise ratio, you can show that the errors have a Gaussian distribution around the true value of the parameters, where this Gaussian distribution is described by a certain matrix that you can build by taking the derivatives of the signal with respect to the parameters. and combining these derivatives with the noise of the detector by computing this integral in frequency space. Now, in this way, you can build what is called the Fisher matrix. And by taking the inverse of the Fisher matrix and looking at the diagonal elements, you get an estimate of the errors on the parameters. Now, Michele is here, and he did some work on the limitations of this approach, but it's a very good first cut on the kind of errors that you can get from the observation of gravitational waveforms. And by carrying out the calculation for ring-down waveforms, what you discover is that the errors depend crucially on the quality factor of the oscillation, not surprisingly, because the quality factor determines the amount of energy, basically, that you can put into a given mode. And so they also scale with the inverse of the signal-to-noise ratio. And now, remember that the signal-to-noise ratio is proportional to the amplitude squared, so it's proportional to if you have a certain ring-down efficiency, a signal-to-noise ratio will scale with the square root of the ring-down efficiency. So now, if you have a black hole which is oscillating, you can determine the quality factor from black hole perturbation theory. And here I'm showing the quality factor as a function of the rotation rate of the hole. Down here, you start from the Schwarzschild limit, and as you increase the rotation of the hole, the L equal M equal 2 mode has a quality factor which is increasing. And if you consider the limit in which the quality factor is much larger than 1, then you discover that the error on the spin of the black hole scales like Q over Q prime, where Q prime is the derivative of Q with respect to J. So naively, you expect, since the quality factor is increasing with spin, that your error is going to go down as spin increases. And in fact, this turns out to be the case for modes which are co-rotating, which have positive M. And now, if you actually do the calculation in a more exact way, what you find is that this is the error on the mass, this is the error on the angular momentum, and the error on the mass becomes larger than the error on the angular momentum, a value of the spin parameter around 0.8. This plot, notice that what I show in this plot is rho times the error. So this plot is universal in the sense that it can be applied to any detector, rescaling by the signal-to-noise ratio. And in the following slide, I will show you what happens when you fold in the information about the signal-to-noise ratio of Lisa. These are the errors that you get typically. So the solid line refers to a non-spinning black hole. The dashed line is a black hole with spin 0.8, where the error on mass and angular momentum were crossing. And the dashed dotted line refers to a black hole which is near extremal. Now, the interesting thing about this plot, here I'm considering a source which is located at 3 gigaparsecs, is that for masses larger than 10 to the 5, the error is always below 10 to the minus 2. So in principle, if you detect a ring-down waveform, you can determine the mass and the angular momentum of the hole with amazing accuracy for astrophysical standards. Now, what we really want to do is multi-mode ring-down detection. I will skip this slide because I don't have much time. But when you look at, when you want to carry out a test of the Kerr nature of your source, what you want to do is not only measure one frequency, you want to measure two frequencies, and you want to measure them accurately enough that you can tell that the two frequencies are different. So suppose that you are measuring two modes, a mode with frequency f1 and the second mode, which is probably less excited than the first with frequency f2. The criterion to be able to resolve the modes is a criterion which is similar to the Rayleigh criterion in optics. So what you want to do is you want to have a separation in frequency which is larger than the maximum error on each of the two frequencies. And if you multiply both sides of this equation by the signal-to-noise ratio, you can obtain a criterion on the critical signal-to-noise ratio that you need to be able to resolve the frequencies of two modes. Now, of course, the same kind of reasoning applies to the damping times. So if we want a minimal criterion to do no-hair tests looking at ring-down waves, what we require is that these conditions are satisfied. And of course, you can have a minimal resolvability criterion when you can resolve either the frequency or the damping time. And you can have an optimal resolvability criterion when you can resolve both the frequency and the damping time. And also, in fact, before carrying out this kind of test, you would like to be able to tell that there is a second mode in the waveform at all. So suppose that you have a first mode with amplitude unity, and you have a second mode which has amplitude, relative amplitude A, which is much smaller than unity. You want to be able to test the hypothesis that your second mode is actually there. And this is going to give you yet another criterion for resolvability of the two modes. So that's going to be an amplitude resolvability criterion. And when you carry out the calculation using the best information available from numerical relativity, these are the critical signal-to-noise ratios that you get. Look only at the solid lines. The solid lines are the signal-to-noise ratios that you will need to resolve the fundamental mode, which turns out to be the second mode in terms of ring-down efficiency, from the L equal M equal 2 mode, which is the dominant one. So the solid line shows you the critical signal-to-noise ratio that you need to resolve either frequency or damping time. The solid blue line is the signal-to-noise ratio that you need to test the hypothesis that your waveform contains more than one mode. And the red line up there is the signal-to-noise ratio that you need to resolve both the frequency and the damping time. So the bottom line is that your bottleneck is represented by the blue line, because that's what you need to test the hypothesis that you have two modes there. And the typical signal-to-noise ratio that you need is of order 30 or so for non-spinning binary black hole mergers with mass ratio Q. This plot is as a function of the mass ratio of the black holes that are merging. So a signal-to-noise ratio of 30 is perfectly well achievable both with LIS and with Earth-based detectors. Now, I will backpedal a little bit, and now I will tell you where the numbers come from that we used in the assumptions to produce that plot.
So that level is what you need to be able to say that that you can see two modes. Mm-hmm. But then to actually do a nice test of the R.
Well, that's actually the signal-to-noise ratio that you need to measure the two modes with an accuracy high enough that you can tell that their frequencies are different. So you're doing a test of GR in that case already. Yeah, it's the usual thing. It's pretty much the same as with MRIs. It's not really a test of GR. It's a test of the Kerr metric, if you like. So now, in that plot, what we used are numbers that come from numerical relativity simulations. And now I'm going to give you some details about the numerical simulations that we studied to come up with estimates for the final spin of the holes and for the ring down efficiency. Now, the numerical simulations that we looked at are numerical simulations by the Jena group. And this is a typical simulation of two black holes starting from quasi-circular orbits with a mass ratio Q of 2. So what you see here is the modulus of the real part of one component of the bioscalar. Now, you know that the bioscalar is related with the amplitude of the waves by two time derivatives. You can decompose the bioscalar into spin-weighted spherical harmonics, and we're looking at these, at the modes of this decomposition as functions of time at some fixed extraction radius, which is supposed to be at infinity. It's not, but it's close enough. So once you have these modes of the bioscalar as a function of time, what you can do is you can compute integrals of these modes of the bioscalar and build some quantities DLM, which are the multipolar components of your radiation. So given the components psi LM of the bioscalars, you can deduce the energy ELM, which is going into each of the components of the radiation. And when you do that, well, okay, by summing those components, you can also get the total energy radiated. Okay? And what I'm showing here is the total energy radiated as a function of the mass ratio of the holes. And what you can see is that the total energy radiated scales with the mass ratio in a certain way, and you can try to fit the behavior by power loss in eta, where eta is the symmetric mass ratio. It's basically the reduced mass divided by the total mass of the binary. And what you find is that the total energy is very well approximated by a quadratic fit in the symmetric mass ratio. So that's one piece of information that we get from the study of these simulations. Another piece of information is the final spin that is produced as a result of the merger of two holes with an equal mass. Now, these are the numerical results obtained by quasi-normal mode fits of each of the components of psi LM, and also by using energy balance arguments. And as you can see, the two different estimates agree very well with each other. And then, once again, we try to fit these results by some polynomial in this quantity, which is, again, the symmetric mass ratio. You can show that they are basically the same.
What's the error bar you showed there?
The error bar is determined by Richardson extrapolation of the numerical results for different resolutions. Yes, it's a convergence test of presentations. Now, what we try to do is look at the final spin. We first realized that the final spin was well fitted by this kind of polynomials in eta, where eta is q over 1 plus q squared. And then we also tried to fit the angular momentum which is emitted after the ISCO. And we realized that pretty much the angular momentum emitted after the ISCO is given by this component. And then we looked at the relation again. We noticed that this number is really, really close to 2 square root of 3, which is the specific angular momentum of a particle at the ISCO of a non-rotating Schwarzschild black hole. And in fact, it turns out that this idea works remarkably well for all binary black hole mergers. And people have used this idea to fit the final spin from a variety of simulations. So, for example, here I'm showing the results obtained by a more, so our results would be the ones along this line here. And the results that I show here are the final spins obtained by the AI group as functions of the symmetric mass ratio, again, nu, which is m1, m2 divided by m1 plus m2 squared, and as a function of A, where A equals A1 equals A2 is the Kerr parameter of each of the two holes doing the merger. Okay? So they assume that they have two holes with equal Kerr parameters, changing mass ratio. They carried out a number of simulations, and they realized that you can fit these results pretty well by some polynomial, where the 2 square root of 3 appears here again, and this determines that you will have in the at point particle limit. Now, well, you can count them. It's 1, 2, 3, 4, 5. Okay, so it's a 5-parameter fit. And also, this fit in principle is not working for when A1 is different from A2, but you can extrapolate the fit to the whole parameter space by performing this substitution. And it turns out to be in very good agreement with another model, which has been proposed by Bonanno, Kidder, and Lehner, where the idea is once again to look at the final angular momentum as a sum of an orbital contribution plus the spins of the two holes. And this model has no free parameters, and it has been shown to be in very good agreement with basically all the numerical simulations that have been done so far. In fact, they also came up with some predictions. For example, they predicted the critical. Suppose that you have two black holes coming together, and the orbital angular momentum is pointing in the plus z direction. And then the two black holes have Kerr parameters which are pointing downwards, and they are equal. And they are given by this chi initial, which is the Kerr parameter of each of the two holes. Now, there will be value of this Kerr parameter for which you can produce a final black hole which is Schwarzschild. When the two holes have very large Kerr parameters pointing downwards, you balance the orbital angular momentum and you produce a non-rotating hole. And they made predictions for the critical relation between the mass ratio and the downward pointing Kerr parameter that you need to produce a non-spinning hole. We went ahead, we did numerical simulations for mass ratio of 4, which is down here, and we found that the prediction works remarkably well. You produce a Schwarzschild hole within numerical errors. So the bottom line of this slide is that we now have control on the final spin, which is produced as a result of a merger of black holes with unequal masses and aligned spins. And also from these simulations, it turns out that there are some interesting results in terms of relativity. For example, it's basically impossible to produce negative singularities, even if you have black holes which are both pointing upwards with extremal Kerr parameters, and you include eccentricity in the merger.
The liner, is it only for aligned spins?
The plots that I've shown are only for aligned spins. They have a slight generalization of the model that only works in the case of simple precession in the apostolatos et al. Terminology. So they have a generalization that works for generic tilt angles, but only when the masses are equal or one of the two black holes is non-spinning. But I didn't discuss it here. Now, okay. So one ingredient that I told you about was we needed to know the spin. And now I've shown you that we do know the spin. These ugly equations here are post-Newtonian equations. So they are post-Newtonian waveforms projected onto spin-weighted spherical harmonics. And what you see from these analytical expressions is that the amplitude of the waves, psi Lm, depends on certain mass combinations. And in particular, for a quasi-circular in spiral of two black holes, you expect the components which have odd values of m to be suppressed when the mass ratio is close to 1, because the mass difference between the two holes goes to 0. And now this analytical prediction turns out to work remarkably well. In fact, here I'm showing you the result of the energy distribution in different multiples L as a function of the mass ratio of the binary Q. And so I'm changing basically the mass ratio between the two holes in this binary. And when the mass ratio is close to 1, the L equal 3 component, which is dominated by L equal m, is strongly suppressed. And also the L equal 5 component is strongly suppressed. But as the mass ratio deviates from unity, all the components are quite excited. And in fact, typically the L equal m equal 3, as I said before, is the subdominant with respect to L equal m equal 2, and it's excited to, say, roughly 1 order of magnitude less than the dominant component. 1 order of magnitude less in energy means a factor of 3 in terms of amplitude, which is what we used for the estimates that I've shown you before. Yes? No, this is actually a full simulation of merging binaries with an equal mass. And we computed the energy in the different multiples by performing the integrals that I've shown you before on the components psi Lm of the bioscalar. So these are pure numerical results. And we explain basically this dip down here by the post-Newtonian arguments that I gave you before. When you have binaries that have equal mass, you expect from post-Newtonian theory that the odd m, hence odd L components are going to be suppressed. Okay? If you want, I can explain. Sorry that I've been confused. So now I'm not going into the details of this, but there's a variety of numerical simulations of merging binaries out there, and for all of these binaries, we can perform the same kind of analysis. For example, you can take two binaries that are moving equal mass, so two equal mass black holes, non-spinning, which are going around in a quasi-circular orbit, and you can reduce the linear momentum on each hole. So you transition from a quasi-circular in spiral to a very highly eccentric in spiral, and eventually when the linear momentum on the two holes goes to zero, you have a head-on collision. And this is the distribution of the radiation that you see as you change the linear momentum on the holes. And you can also play the same kind of game with funny configurations of the spins, like you can take spins which are pointing outwards from the page, or inwards, and that are pointing in funny directions that maximize the kick. And you can get the energy distribution in all of these different scenarios. We didn't know this a couple of years ago, but now we are able to do predictions, and they seem to work pretty well. Now, the numbers that I've shown you so far are numbers for the total energy radiated in the whole merger. From the moment we start the simulation, when you have a binary going around, to the end where you have a single black hole which is vibrating in the quasi-normal modes. But if I want to plug a number into my ring down efficiencies, what I really need is not the total energy radiated in the merger. It's the energy which is radiated in ring down waves. And now, this is a problem because we don't know how to define the ring down regime. We don't know what the ring down starting time is. Now, a useful criterion which has been proposed by Nollert a few years ago is to compute a quantity that he called the energy maximized orthogonal projection. Basically, the idea behind this energy maximized orthogonal projection is to do match filtering in white noise. So you take a ring down waveform, which is given by this analytical expression, and you slide it on top of your component of some numerical relativity. So you have a numerical relativity simulation, you extract components of the biscalar, and you slide your quasi-normal mode waveform on the component of the biscalar until you maximize some integral that gives you the energy going in the quasi-normal mode template. This is basically match filtering with white noise. And what you see is that the fraction of energy that goes into ring down is not a maximum as you would have naively expected up here. It's in fact a maximum slightly before, because the waveform looks like a ring down all the way down to this point, and then it starts looking different. It starts looking like an in-spiral again. And quite surprisingly, for all the simulations we tried, the fraction of energy going into ring down waves is roughly of order 42%. So when we look at these unequal mass binary black hole mergers, the typical numbers that we get for the ring down efficiency are between 2% and slightly less than 1% as a function of the black hole mass ratio. And this is where the 1% that I used in the previous slides comes from. It's actually confirmed by this criterion and by an analysis of numerical relativity simulations. And also notice that as we increase the mass ratio out of unity, when we look, for example, at a binary which has mass ratio of order 4, the L equal M equal 3 mode carries about 11–12% of the energy. Okay, now what I've shown you so far is that numerical relativity simulations can be used to predict the spin, the final spin, and the energy distribution of the gravitational radiation resulting from a merger.
If you were to do the opposite and look how much energy goes into spiral-like waves, is there anything left in between? Or
this is a question that Alessandra has looked at. There is a very small thing left in between, which you can call the merger. But it turns out that the energy, if you really want to split your waveform into in spiral, merger, and ring down, there is still a very small part which is merger. But in fact, by using yes, for non-spinning binary. So this is very academic because you can always take a superposition of quasi-normal modes and push your ring down part backwards by including more and more modes. We can talk about this later. It's really technical and not particularly illuminating on the physics. But so now, one thing one can study by using these results from numerical relativity simulations is the spin growth of black holes during during their cosmological evolution through accretion and mergers. Now, this plot that I'm showing is from a paper published a couple of years ago by Marta Volonteri and others. And in this paper, they were studying the evolution of all black holes in the universe due to mergers and accretion. Now, for mergers at the time, they didn't have numerical relativity simulations. And what they used were results obtained by Scott Hughes and Blanford by extrapolating point particle results. So Hughes and Blanford were looking at particles falling into curved black holes, and they were saying, oh yeah, these results should be appropriate for small values of the mass ratio. Let's suppose that they are valid all the way to mass ratios of order unity, and let's get some prescription to get the final spin resulting from a merger. Now, by using this prescription and some prescriptions for accretion, Marta and the others were able to obtain histograms that show you the fraction of black holes which have some given spin out of the total population of black holes in the universe. And these are snapshots of these histograms in different redshift intervals. So they obtained some answer, and basically their answer at the time was that the critical physical element that produces fast spin in black holes is not merger. In fact, merger on average tends to spin down the holes. What produces fast spin in the holes, according to their model, is accretion. They consider two different models for accretion, one in which you have thin disks. In this case, they found that a very large fraction of all black holes out there should be nearly maximally rotating. And then they considered a different model for accretion, in which you have a thick disk, and the accretion is not so efficient in spinning up the holes, but it's still efficient enough that most black holes have very large spins. Now, this paradigm that accretion spins up the holes has been challenged recently. And some people came up with different models of accretion in which accretion occurs in a stochastic fashion, and the disks are tilted with respect to the direction of the hole, and they don't produce very fast spinning black holes. So, but now we know what we can expect for the outcome of mergers in terms of the final spin. So just yesterday, Marta sent me some results in which she is ignoring the spin up due to accretion. She's considering that all spin evolution is due only to mergers. And you start with black holes that are non-spinning, and you let them merge using the results from numerical relativity that I've shown you before. Now, if you assume that the black holes are aligned or anti-aligned with 50% probability, what you get is initially a distribution which is peaked around 0.6, which is the final spin that you get for the coalescence of two roughly equal mass which are non-spinning. So this is reasonable. This is the result from you would expect from numerical relativity. You have two black holes merging, and you get a peak here that corresponds to the final spin that you would get. But then, as the cosmological redshift increases, you keep on having mergers between black holes of different masses, and this produces a smoothening in your distribution of spins across the universe. And what you see is a very nice feature. There are no black holes here. You have no way of producing very fast spinning black holes by merger only. And things will change if you consider an alternative model in which has been proposed by Bogdanovich and others at the University of Maryland, in which the accretion disks around the holes act to align the spins on each hole with the orbital angular momentum. In this case, every time you have an accretion event, both black holes are pointing upwards, and in this way you can still get maximally spinning black hole. But the bottom line of this game that we played is that a single observation of a very fast spinning black hole can rule out some models of accretion, which is very nice, and we're planning to push these ideas a bit further. Now, probably how much time do I have? 10 minutes, okay. Thought it would be worse. So now, what I'm showing here is work related to what Lisa Goggin is doing here in the analysis of LIGO data. The idea is the following. I've shown you before that depending on the particular merger scenario we're looking at, you can have the excitation of more than one mode in your actual waveform that you want to detect. And what I've shown from the numerical relativity simulations is that if you take the ratio of the second mode in a pair with respect to the first, this ratio is typically of order 0.3. Now, the game is actually dirtier because each mode, say the L equal M equal 2 mode and the L equal M equal 3 mode, will have a different angular dependence. So the radiation observed at different angles is going to look different. But suppose that we average on angular functions, and we assume in our toy model that we have a very simple superposition of two damped sinusoids. Now we say our real waveform is made by a superposition of two damped sinusoids, and we try to detect this waveform by a template that consists of a single damped exponential. And we can compute the fitting factor for our template, and from the fitting factor we can compute the percentage of events we would lose by using a single mode template to detect a two mode waveform. And this is what you get for the percentage of events lost as a function of the mass of the hole for initial LIGO and advanced LIGO. Now, what happens is that as the black hole mass increases, the number of events lost increases as well. And you get a good idea of what's going on when you look at the parameters in your template that produce the largest fitting factor. So the blue lines here are the real part of the quasi-normal mode frequency of the fundamental mode and the quality factor of the dominant mode predicted by theory. And then what the black line shows you the value of the real part of the frequency for which the filter achieves the largest fitting factor. And as you can see, there is a slight bias in the real part of the frequency, but it's not something we should really worry about. It's a bias of order 1% or so, which is still very well acceptable. But the quality factor of the oscillation is very highly biased. It turns out to be 2.5 when it should be 3 or so. And this is because the second mode is sort of cheating our, it's cheating our filter, and it's trying to convince our filter that the slope of the ring down is slightly different from the one it should be. So we get a different quality factor, but now the quality factor is the quantity, is a dimensionless quantity, and as such it can only depend on the spin of the holes. So a large bias in the quality factor means that we're going to have a large bias in our estimate of the final spin of the hole. So the bottom line is match filtering detection of ring down waveforms with a single mode template is good enough in terms of fitting factor. We can use it. But it's not good enough if you want to do parameter estimation. If you want to do parameter estimation, you have to do something better. Now, in this plot, I'm making a simplifying assumption. In principle, you should have two phases here describing the relative phasing of the two modes in the pair. And here I'm just assuming that these two phases are at 0. In fact, what I should do is something more similar to what people do for inspirals. We should assume that we have complete ignorance on the relative phases of the two modes, and then compute a minimax overlap where you maximize on the frequency and the damping time of the oscillation, and then you minimize on the values of the unknown phase angles phi 1 and phi 2. So if you do that, you can get very nice contour plots of the fitting factor. I'm playing again the same game that I was playing before, but now I'm changing phi 1 and phi 2, and the filter is maximizing all of its parameters to obtain the largest fitting factor for each assigned value of phi 1 and phi 2. And these are contour plots of the fitting factor as function of the two phi angles for a binary of 200 solar masses as detected by advanced LIGO. And what you can see here is that the fitting factor can go sensibly below the typical limit which is considered acceptable, which is around 0.965. So you can actually lose more than 10% of the events because your filter is getting confused by the relative phasing of the two angles. And the minimax overlap is the one that will correspond to minima islands of minimum fitting factor here. So if you do a minimax overlap, this is where your detection is going to happen. And now you can ask the question, if I have a detection here, what kind of bias am I going to have on the parameters of the hole, or on the frequencies and damping times of the quasi-normal modes? Now, for this particular hole that we were looking at, the first mode in the pair had a real part of the frequency of 0.5, and the second mode in the pair had something like 0.8. And as you can see here, the contour plots of the frequency that I get are not very different from the dominant mode in the pair. I'm always getting the frequency right, so I shouldn't be worried about the frequency. But what happens to estimates of the quality factor? Now, estimates of the quality factor range from about 2 to about 5 when the quality factor of the first mode was 3 and the quality factor of the second mode was about 4.5. And the minimum in the fitting factor roughly corresponds to this island here, where my filter is actually detecting the L equal M equal 3 mode. It's detecting the second mode in the pair. So the caveat, the lesson one should learn from this exercise in match filtering is that we should be really careful if we want to do parameter estimation by using single mode template waveforms. Because very easily our filter is going to get confused, and if I do a minimax overlap, I will end up catching the wrong mode. Now, a better idea for doing parameter estimation would be, okay, I can do a detection using match filtering, and then I do post-processing. And to do post-processing, I can use different techniques. What we did was we went out there and we did a literature search, and the engineers have studied this problem in very high detail. They came up with very efficient methods to detect, to estimate the frequencies and damping times of damped exponential Z noise. One method which is ideally suited for this kind of problem is due to a French guy, Baron de Prony, and it was invented back in the 18th century. And it has been improved and readapted in more recent times. I won't tell you how it works, but I will tell you that it seems to do a pretty good job. And in fact, we tested the method on numerical relativity simulations, and we've been able to extract the spin from numerical relativity simulations quite accurately. How much time do I have? 2 minutes. Okay. So, what do I want to tell you? Okay, I can tell you something about how these Prony methods work in extracting the final spin from numerical relativity simulations. What you can do is you can play the following game. Suppose that you look at the L equal M equal 2 component of your radiation, and you have psi Ln for L equal M equal 2. Now, you try to estimate by using Prony methods the quality factor of the oscillation for the L equal M equal 2 waveform. You will get some number. Now, the quality factor is a unique function of the spin of the hole. And you can use perturbation theory predictions to invert the relation, the functional relation between Q and J to get J as a function of Q. Okay? So, in this way, you get an estimate of Q from Prony methods. You invert the functional relation, and you get an estimate of the spin. And by playing this method, you get the black solid line here. Now you can repeat the same game with the L equal M equal 3 mode. The L equal M equal 3 mode is less excited, and it's going to be affected by numerical error much more than the first mode. So your estimate of the quality factor is going to have larger bias, and your spin is going to oscillate around the real value with a larger oscillation amplitude. But by cross-correlating the information from the different multiples, since you know that this is general relativity and the spin of the hole has to be unique, you can get a best guess for the value of the final spin of the hole. And what happens is that if you look at simulations which have different numerical resolution, as you crank the numerical resolution, the oscillations go down. So we are still left wondering if the oscillations that we see are real nonlinear effects. So our black hole is really oscillating in a way which deviates from the predictions of linear black hole perturbation theory, or if the effects that we are seeing would disappear when we research and extrapolate the results to infinite resolution. And this is something that probably our numerical relativist friends at Caltech here are going to be able to answer when they get the merger, because their resolutions wouldn't be affected by numerical errors as much as the simulations we were looking at. Okay, time over? Yeah, I guess, well, there is only one thing. I'm just going to talk about this very qualitatively. We've been looking recently, motivated by scenarios of mini black hole production at the LHC, at numerical relativity simulations in which you start with two black holes which have very large momenta pointing towards each other, and increasing the momentum on these two holes, trying to get the total energy radiated as the black holes become ultra-relativistic. And the motivation for this study comes from the prediction in string theory motivated TeV gravity scenarios, the prediction that if the scale of gravity, that the Planck scale is lowered to a TeV, you will have production of mini black holes at the LHC. So the idea is to model, you have two particles which are colliding at the speed of light and they form a black hole. Since these particles, the energy of these particles is dominated by kinetic energy, you can presumably model them by black holes which are boosted near to the speed of light, because the internal structure of the objects is not going to matter so much. And in this way, you can get an estimate for the total energy radiated when these two particles collide and form a mini black hole. And we are doing the simulations these days, and we're putting all the numbers together and trying to extrapolate to what you would get when your gamma factor tends to infinity. And what we get is that the energy radiated seems to be very close to 29%, which is the limit predicted by the area theorem. If this is true, it's extremely exciting, because it means that the most relativistic process you can think of in the universe, which is head-on collision of two black holes at the speed of light, produces as much gravitational radiation as you can imagine to be produced in the collision of two black holes.
That actually puts new meaning to the word black holes are black, because their area, their cross-section is equal to their area.
Right, exactly.
Which is what, when we say that, when we collide protons and their cross-section saturates the physical area, we say the protons are black.
Right.
That's interesting.
So that's just a curiosity that I wanted to throw at you at the end of the talk. This is a short summary. You can just read through it. And I'm sorry that I ran out of time. And thanks.